Okay. Okay, so I would also like to start with thanking the organizers, Benedict in particular, for inviting me to this really enjoyable program. And so what I would like to talk about is the solution to an old problem of Hitler's last college. So I will talk about order types of chains. Let me shorten my title of functions. So what kind of functions am I going to talk about? So throughout the talk, X is an uncountable Polish space. That is metrizable, completely metrizable and separable topological space. And chains are going to mean chains with respect to the pointwise ordering. But let me point out subtleties. So, okay, it's obvious, but let's say we have two functions. All functions in this talk are real valued. Then we say that f is less than or equal to g pointwise, but these are functions. So strictly less means not that they are strictly less everywhere, but it means that they are less than or equal to everywhere, and there is at least one point where they disagree. So if and only if for every x in x, f of x is less than or equal to g of x, and there exists...
f is not equal to g.
Yeah, f is not equal to g, exactly, but I want to emphasize this, yeah. F of x is a straight or not equal to or whatever. So you know what I mean. But so the picture really is that I do not want these kind of chains, but I want these kind of chains. Somewhere bigger, and this plays a very important role, of course. Okay, so this is the ordering I'm going to consider and going to be considering. And so what type of questions we are going to look at? So well, this is sort of the general question. Let's say we have a class of functions, say the class of Borel measurable functions on X or something like that. So in general, but of course I won't use it in the generality. So this is a class of functions. And then this becomes, with this ordering, this becomes a partial order, a function class. So what can we say about it? Of course, this is too vague, but let me just ask this first. Post set, the partially ordered set. F with respect to this ordering. Yeah, this is clearly too vague. But so, for example, I'm going to be looking at function classes like C0, 1 with this ordering, or this is the Borel sets, Borel functions, I'm sorry, with this ordering and so on. And in the generality, you cannot say much. Then you restrict yourself to simpler questions, right? One of the simplest ones you can ask is, okay, are these the same? And this is too easy. I mean, there are tons of ways to answer that this is not the same, but let me do it in a very specific manner. And before I do that, I need a definition. So I'm going to say that the partially ordered set is embeddable into another one if there is a strictly monotone map. But I have to warn you that this does not mean that the second one contains an isomorphic copy, because a strictly monotone map may well send incomparable points to the same element. So, okay, so P less than a partial order. Okay, sometimes I put this P is embeddable into Q in this talk. I will use the term embeddable. but this is quite misleading. If and only if there exists a strictly monotone map. So P to Q such that for every P prime in P less than P prime implies phi of P less than in Q phi of P prime. Okay, so yeah, remark maybe non-monotone, non-injective, I'm sorry. But in many instances, I'm going to use it for linear orders. I mean, if P is a linear order, then this is just an isomorphism. So P is linear. Okay, is a linear order. And this implies that our phi is an isomorphism. It is injective, so it's an isomorphism. So embedding of linear orders is really what we think an embedding should mean. Okay, and so let's just go back to this question. So why are they non-isomorphic? But of course, they're obviously non-isomorphic for various reasons. But I just want to go to this direction. So fact, obvious fact, C01. Let me drop this ordering if it's clear from the context. That's just not isomorphic to the Borel set, Borel functions, because one of them contains an Aleph1 and an omega-1 type increasing chain, and the other one doesn't. So it's obvious. Since omega-1 considered as a partially ordered set, but you know what I mean. It embeds into the Borel functions, but omega-1 does not embed into the continuous functions. And why is that? Let me just...
Actually, I was expecting that you're going to say something else.
Yes.
C01 is R embeddable, the other is not.
This is what I'm going to say somewhat later, of course. And this is this is the easiest proof, actually, right? So okay, there are tons of proofs to show this, but the easiest one is that R embeds C01 and then you're done. Yeah, this is just this motivation part, and I just want to, okay, so it's not, yeah, these are 2 easy problems. Okay, so, but still let me just remind you the proofs, how to find this, quite obvious. Let's just fix X alpha in 0, 1 for alpha, no count of ordinals distinct, and define F alpha as what is it, the characteristic function of the first alpha many points. Right, so these are Borel sets, these are countable sets, characteristic functions of countable sets. Borel, and it's clear that as alpha is increasing, the sets increase, so the functions increase. So this is obvious. And the other one, the other direction, so why you cannot find such a Aleph1 sequence in C01. The reason is that C01 is R embeddable. So assume that F alpha alpha less than omega-1 is a strictly increasing transfinite sequence. And what do? Then you R embed C01. So then if you look at R embedding is easy. The easiest. There are various ways to do that, but the integral is the shortest one, I guess. Is a strictly increasing Aleph1 sequence in R. And we know that in R there are no Aleph1 sequences, so this is a contradiction. So this is very simple. Okay, but what I wanted to get out of this was that there is a natural question here. If you want to understand these posets, so how do the well-ordered chains in these posets look like? So this is the warm-up problem to the actual Latzkovich problem I'm going to consider. Describe the well-ordered subsets of these posets. Okay, but we are already done for C01. Let's take a back. Okay, so this is, hence we arrive at our general question 1. Okay, alpha is an ordinal. Alpha is embeddable into your function class. So what is this? This is the question. What ordinals? What order sequences show up in your post set? And yes, as I just mentioned, alpha embeds into C01 is already quite clear if and only if alpha is a countable ordinal. This is clear. Yeah, we have seen that LF1 is not possible, but every countable ordinal are embeddable. So if constant functions, you can do that. So it's very easy. But let's take one step further. The Borel sets are much less clear, right? So okay, LF1 shows up, but it's already unknown if LF2 shows up or not. So LF2, whether there's an LF2 sequence for Borel functions, this is independent of ZFC. This is all very classical and very easy. But just out of curiosity, let me remind you how these things typically work. So okay, so first, this is classical. It is not that simple at all, but maybe Steve will correct me, but I think it first appeared in Cunan's thesis that there is no LF1 chain in the Cohen model. So this is the first thing. Cohen model. No LF2 chains of Borel sets in polyspaces. And let's assume that we have an LF2 chain of Borel functions. Let's look at their subgraphs. Then in X cross R, you have an LF2 type chain of Borel sets, which is not possible. Okay, and what is the other thing? What is the other thing I wanted to take about? It is also consistent that lots of things show up. And what's the reason behind? What's the reason behind? The reason behind is that this is also a well-known fact. This partial order, P omega with the almost containment, so containment mod finite. This partial order is embeddable into the Borel functions. Okay, and we know that many complicated things can be embedded here. For example, consistently omega 2 can be embedded here, and then it shows up here. And so how do we do this? How do we do this? And this will also take us to the next topic we want to talk about. So actually, what we do is that P omega with this almost containment can be embedded into the sigma 02 means the F sigma subset of this topological space with its usual Polish topology. And the partial order is just the containment of sets. So this is the first step. How do we do that? Whenever we have an infinite subset, we assign to it the following. Those subsets of those subsets of omega such that B is almost contained in A. Okay? I'm claiming that this is a strictly monotone map. That's obvious. I mean, if you increase A, then this becomes larger, obvious. But we also have to check that this is always F sigma in this topological space. This is F sigma, but this is obvious. I mean, this just says that there exists an N such that after that N, B is a subset of A, which is there exists an N is where the sigma comes from, and everywhere after that, B is a subset of A. It's a closed condition. So this is clear, and then what do we do? Okay, then it's obvious from this that we can get to this sigma, F sigma subsets of the closed interval ordered until inclusion. Why is that? Because this topological space is almost a subset of 0. It's homeomorphic to the subset of 0, 1. So every set that lives in here can be considered as a subset of 0, 1, and then you're done. And then to every set A, you assign its characteristic function A, and then you get a Borel set, right? So it's easy. Okay, but it is not just that you got some sort of Borel set. This is the next thing I wanted to say.
Function.
Oh, sorry, Borel function. This was the Borel set. It's not just a Borel function, but it is a very, very low complexity Borel function, right? Characteristic functions of F sigma sets. So, so actually, what we got was that they can all be chosen to be Baire 2 functions. Okay, because the next step will clearly be that Borel sets are very complicated. You cannot really hope for a very nice characterization. So people started working on the Baire hierarchy between the continuous and the Borel classes. And this already shows that even if you go down from Borel to Baire 2, you still have this phenomenon. So very complex things can show up. Yeah, I keep confusing sets and functions. So maybe I should pause for a minute. And note that this is not just a coincidence, but somehow, in this talk I will try to talk more about functions, but there are two parallel theories here. Either you can talk about functions under the pointwise ordering, or sets under containment. And I've already mentioned this, so it's lots of obvious things I say, but if you're talking about characteristic functions, then this pointwise ordering just translates, of course, to containment, right? So whenever I talk about, say, Baire 1 functions, or I don't know, Baire 2 functions, and chains under the pointwise ordering, if I restrict myself to characteristic functions as a special case, this includes the case of certain sets. In case of Baire 2 functions, it is the delta 0, 3 sets under the pointwise order and under containment. So if you're not so much interested in pointwise orders and chains, then just translate every single statement and then theorem I said to chains of sets. And maybe they are even more popular than these topics. For example, everyone knows the statement that in a Polish space, closed sets under inclusion cannot form an omega 1 chain. This sort of translates to the continuous case, and Borel sets under inclusion can form this chain and that chain. Such statements just translate to pointwise ordering here. So sets and functions are sort of interchangeable in this talk. Okay, let me check. What else did I want to mention? Okay, so yeah, the next thing is that I haven't yet defined formally Baire 2. So the next thing is that from Borel I want to climb down to a class that's more reasonable. So just for the record, recall that B1x is the Baire class 1 functions. I guess everyone knows it, but I'm sorry. Baire class 1. And that simply means that pointwise limits of continuous functions and I'm not really going to use the Baire hierarchy, but Baire class 2 means the pointwise limits of Baire class 1 functions, and so on and so on. Okay, and so this whole remark was to convince you that Baire 2 is very complicated already. I mean, it contains this one, so it's not easy to. Okay, I said this already. So let's go to Baire. This sort of all implies that Baire 1 might be the only interesting question left when we are interested in these well-ordered chains. And indeed, prominent mathematician Kuratovsky already considered it and proved that an ordinal is embeddable into Baire 1x. X is an uncountable polyspace if and only if countable. This is a non-trivial proof that Aleph1 is that the Baire functions do not contain Aleph1 chains. I'm not saying it's very difficult, but this is clearly a non-trivial proof. Okay, if we go back to our naive,
What's the date of the theorem?
I think it appeared in his book. That's the only source where I have seen it, in his book, The Topology. I'm not sure where when the first edition was published,
Okay.
but yeah. So this is all we can say about the well-ordered chains. But if we go back to our naive motivating problem, how to distinguish between the partial orders, then this still leaves one option. This still leaves one option open. So could that be, well, of course not, but still, it might cross one's mind. Could that be that these two things are isomorphic, these two partial orders? Because the chains, these well-ordered chains, do not distinguish, yes?
You always, this translation that you put here is not isomorphism, it's inter-embeddability.
No, I mean isomorphism. I mean isomorphism of both sets, because I think that's a better, you're right, I could also talk about that, but I think this is a better motivating problem. It's such a natural question. You have two posets, are they just isomorphic as posets? But you're right, I may be even
Okay,
ruling
we have
out
two
embeddability.
questions.
And I'm answering both, and both are obvious. So this is nice.
It's ordering embeddability.
Yeah,
It's
it's,
a quasi-ordering and it's a corresponding translation.
yeah. It could be that, and then these trivial proofs I gave also answer the other question. Yeah, they are not by ambiguity. Yeah. Okay, so why? So what's
For
the?
example, if you're proving that they're not isomorphic, this is a weaker result than if you're proving that they're not.
You're right. But both are quite weak. Both results are quite weak. Yeah. So I'm just I didn't put these into the paper. I think these are good motivating problems for an audience, but these are so obvious. Okay, so the chains, the well-ordered chains do not distinguish between the two, but still we have a nice way of proving that they are not isomorphic or not bi-embeddable also, if you want to. And this is the following: there is a linear order. It's the double interval. So 0, 1 cross 0, 1 with the lexicographical order. Okay, so you double every point of the unit interval and take the lexicographical order. And this is clearly not embeddable into this one, but it is embeddable into the Baire functions. Okay, so this shows why they are not non-isomorphic. And why is this? Why is it that this is non-embeddable into C01? Because C01 is R embeddable, and in R, of course, you cannot continue many pairwise disjoint intervals. So this is quite easy already from this R embeddability thing. And how do we do this? This is just a small picture. Okay, let me write it down. So Fri should be the characteristic function of, Fr0 should be the characteristic function of 0R, and this is open, I guess. And Fr1 should be the characteristic function of the closed interval. Okay, let me draw a picture, maybe I messed it up. So I'm just looking at these type of functions. Here it's 1 up to R, it's, well, either 0 or 1, depending on if we are descent point or descent point, and then it is 0. And it is easy to see, of course, these are Baire functions, no matter how you define the value here. It is easy to see that this is a totally ordered family, and the ordering depends first on R, where you put R. If you increase R, then the function increases. And once R is fixed, then the ordering is decided by this value. So this is exactly the lexicographical ordering. And so this shows that these functions form such a well-ordered subset of Baire, of the Baire class 1 functions.
Not well-ordered.
Not well-ordered, I'm sorry. Linearly ordered and ordered in this specific order type. Yeah.
It embeds, yeah.
And it embeds. And what did I do? Okay, so this leads us to the actual question I want to talk about. I replace this with a linear order. So what kind of linear orders can you find in these posets. Well, because of course you cannot say much about the posets themselves. I mean, describe the structure makes very little sense. But this is a very concrete question, and it may well have nice concrete non-trivial answers. You cannot describe the poset. Describe all the possible linearly ordered subsets of it. And this is what we are going to do. Well, maybe I'm not even writing down, but okay, I write down because I did that so far. So L embeds into the continuous functions if and only if L embeds into R. So C01 contains exactly the real order types, because they are, if you have a real order type, then the constants do it for you, and if you have an order type here, then you embed this into R, and then you're done. So we already discussed this. We also had that P omega it is ordered under almost inclusion embeds into Baire 2. And this implies, hence consistently, okay, so we know, I haven't mentioned it yet, but consistently, this is Parovichenko's theorem, I guess, that consistently every at most continuum sized linear order embeds into this one. So hence consistently, this contains all the possible linear orders you can think of. And consistently doesn't contain omega 2. So, okay, I'm not saying it's impossible to characterize it in a nice way, but this is complicated. So this implies that complicated. I'm not saying it's hopeless to get a nice characterization, but it's complicated. And then there is one case missing out, and this is where my talk starts. This is what Lackovic asked in, I don't know the exact date, because he published it in several papers, but he says it was in the 70s. So what are the linearly ordered subsets of the Baire plus 1 functions? So, okay, L linear order, L embeds into Baire 1, well, X or 0, 1, you will see later that it doesn't really matter. So describe, this is the only case left that seems interesting. Everything else was actually not that hard. What is the Baire 1 case? Describe all the chains. Okay, so what was the known results? All the results, well, all I don't know. Let me list a few. Yeah, of course there is Kuratovsky's theorem. Yeah, Kuratovsky is saying that omega 1 is not embeddable. I mentioned that already. And then Gerlich and Petrushka asked if, could it be that this is the only obstruction? So whenever you have a linear order, not containing omega 1 and omega 1 star, so strictly decreasing omega 1 sequences, could that be that it is embeddable? So only obstruction. No, this was Comiat's result. Actually very elegant, but very short. Oh, I'm sorry. It's just consistently no. The Suslin lines are not embeddable. Baire 1 functions cannot form a Suslin line, and of course they do not contain omega 1 and omega 1 star type subsets. So this is a consistent answer. Actually, I give you the proof in one sentence. This is just one sentence, but it's quite amusing that this is a consistent answer to a question. The theorem is ZFC, let me warn you, and the proof is forcing. Okay, so, but the result is ZFC. So if you have a Suslin line, there's a corresponding Suslin tree consisting of intervals. You just force with it, then you get a branch, and that gives you an omega 1 type sequence of Baire 1 functions, which is impossible by Kuratovsky's theorem. Very short, very elegant. Actually, at this point, Lackovic, who was quite interested in forcing, asked if there is a forcing-free proof, and tried quite hard, but it's not easy to replace this with something elementary. And only until our very recent characterization of a very recent solution to this problem, there was no other proofs known. So this is one line, but still somehow non-trivial and interesting. Okay, and then myself with Yuri Stepras. We did that. We answered this question. That the answer.
Good that it's me.
It's me. Yeah, I have a perfect name for mathematician. Yeah. I put the two dots, but I always enjoy it. Yeah.
Expected that.
Yeah. So it's. So the answer is no in ZFC. So we construct the linear order. I'm not giving you the details because it's not very interesting, not very short. That instead of Sussley lines, you can construct ZFC examples.
But it's stronger than the answer is no, because you have one fixed.
Yes. Okay, that's right. Okay. Yeah. So, and we also shown that under Márton's axiom, this is the only abstraction, as long as you restrict yourself to linear orders of cardinality less than the continuum. So yes, for this is the only abstraction for cardinality strictly less than the continuum. So the theorem is the following. Let me say it in more words than this. So under Márton's axiom, a linear order of size less than the continuum is embeddable into the Baire functions if and only if it doesn't contain omega 1 and omega 1 star. But of course, the C-sized orders are still missing. Yeah, what else was known? Okay, maybe I should stop here and not list too many of the partial results. There were quite a few. But let me list a few questions that were open instead. So what kind of questions were open? Yeah, the one I just touched upon. So L is embeddable into the Baire functions on some Polish space. Does this imply, or is this equivalent to L is embeddable into the Baire function? So does X matter or not? This is the question. If it turn out no, then what? So suppose L is embeddable into the class of Baire functions. Does this imply that L is actually embeddable to the delta 0, 2 sets ordered under inclusion? I didn't say it. So this question asks, this question asks, L can be represented using Baire functions. Can it also be represented using Baire characteristic functions? So are functions and characteristic functions the same? This is what we're asking for, because these are the sets that are simultaneously F sigma and the G delta. So yeah, maybe I should note here that delta 0 2 means that it is F sigma and G delta at the same time, and the characteristic function is Baire 1 if and only if A is delta 0 2. So this is why this question just asks this. You can do some order by functions. Can you do it by characteristic functions? Can you do it by sets? So this is another question. Let me see what else we were interested in and people were interested in. Yeah, all sorts of questions. So L is embeddable. This was the one that was bugging us most. Does this imply, it looks a bit technical, but it was quite important for all the constructions. Can you double the points? And there were all sorts of others. For example, once you have a linear order and a completion, and the linear order is doable by Baire functions, is the completion doable, and so on, and so on, and so on. Okay. Let me not continue. Okay. Yeah, it's getting quite. I'm running out of time. I'm sorry. So here are the answers. And here's the solution to the Lackowicz's problem. So how did we do that? So we came up with one combinatorially defined, I will do it in a minute, a linear order, which turns out to be universal. In what sense? This order can be represented by Baire functions, and if something can be represented by Baire functions, then it's embeddable into this linear order. So there is a maximal linearly order, and this is combinatorially easy to describe so that, for example, you can use it to get all these problems. Okay, so this is the plan. So I have to do some not so pleasant looking notation. So what is this? This is the transfinite strictly decreasing sequences of reals in 0, 1, terminating at 0. Sorry?
Countable.
Transfinite cyclic sequence.
Oh, well-ordered sequence.
Transfinite well-ordered strictly decreasing implies they are countable. Yes.
Yeah, sure.
So this is, well, I will denote them by x bar, which is x alpha alpha less than equal to psi. They have a last element, and the last element always has to be 0. So psi is countable, but yeah. And for every alpha less than beta less equal psi, x alpha is bigger than x beta, and they also have x psi equals 0. Okay? So this is just a set, and let me put a partial order on it. The partial, actually a linear order on it. The linear order will be the following. The lexicographical order would be the natural candidate, but for some reason that doesn't work. That's not what we need. But on the even, so we flip the ordering on the odd levels, and otherwise it's lexicographical. I call this the alternating lexicographical. Okay, so let me write this down. So for x bar and x bar prime over here, distinct, there is a minimal delta where the two sequences split. Note that because they all terminate at 0, and they are cyclically decreasing, there are no sequences extending each other. So all distinct sequences actually split somewhere. Okay, so there exists a minimal delta such that x delta is not the same as x delta prime. Okay, and then we say that by definition x bar is less than, with respect to the alternating lexicographical ordering. This is what we are defining here. If and only if, yeah, then there are two cases according to which delta is odd or even. So delta is even. Okay, I don't have enough space. So 2 divides delta, and x delta is strictly less than x delta bar. Yeah, so on the even stages, I keep the ordering, and on the odd stages, if the splitting happens to be on an odd stage, I should put an OR here. And x delta is, no? Something is wrong. Yeah, I should flip it the other way around. Okay, so this is the definition. So you have these sequences. It's a tree, and it's almost the lexicographical ordering. You just need this one extra tree. I try to explain where it comes from. So it is. I think
that is a linear ordering.
That's a linear ordering. Yes. Yes, I think it could be an objection that this is not a solution to the characterization because this is too complicated or whatever. So this is why I'm listing all these open problems, because using it turned out to be simple enough. So using this, we answered all the existing open problems, and moreover, we gave simpler proofs to all the non-theorems. So I think this is enough to at least convince me that this is a useful characterization. But whether it will be enough to convince the referees, I do not know yet. Okay, so this is the linear order, and here is the theorem. Oh, I should have mentioned at the very beginning that this is a joint work, the joint work with a student of mine, Zoltán Vidnyánszky. And Zoltán Vidnyánszky. Yeah, let me write this down because this is only a theorem in this book. Let X be an uncountable Pauly space. and L a linear order. Then the following are equivalent. L1, L embeds into Baire 1, X2, L embeds into this combinatorially defined object. And let me also put here L, because this is the answer. This is the main part. That's what you were interested in. L embeds into the characteristic Baire 1 functions. So the delta 1, I'm sorry, delta 0, 2 sets ordered under inclusion. Okay, I don't have enough time to write this all down, but as a corollary, now every such problem translates to a combinatorial problem, right? So no, not really. And the first one is just an obvious consequence of this, right? Because this holds for x and this holds for 0, 1, and they're all equivalent to this one. So this one is okay. We don't even have to use the combinatorics of this one here. But for the same here. But for the actual interesting ones, for example, for this one, or for the one I only mentioned, whether completions of representable ones are also representable, it just translates to here, right? We are here. We don't care anymore about continuous or Borel or whatever sets. We have the linear order subset of this. We double the points. Can we embed that back to the original space? Or we take a linear order subset of this, look at some completion. Can we embed that completion into here? And actually is that the duplication is doable. That answer is yes. No, completions no, duplications yes.
Okay.
But this is and this only is the combinatorics of this linear order and nothing else. Okay, so let me not write these down. These corollaries that actually these are quite long. I mean, so the combinatorics is not simple at all. Lots of pages, unfortunately. So of course I won't be able to give the details here. But just believe me, it answers everything we were interested in, and others were interested in concerning this topic.
The paper on the archive.
Yes. Okay, and in my remaining time, I would like to say a few words about the proofs, and of course, the proofs should explain why we have these objects, why we have these objects here. Okay, so ideas of the proof. If I want to be very brief, the whole proof can be. It is a one-line proof. It's just a one-line proof, essentially. So what do we do? Yeah, a remark. Maybe Seb already pointed it out, that we are not only going to prove this, that they have the same linear orders. What we're going to do is that these three partial orders are all bi-embeddable. They are all equivalent with respect to bi-embeddability. This is what we're going to do. This is stronger than just that they have the same linear orders. And how do we do that? So, I need my notes. So this is going to be number one. This is a key step. I will define this object in a minute. This is the very similar to this one. It's just that we don't have reals here. We have upper semi-continuous functions here with the pointwise ordering. But this is what comes up naturally. And this is the second one. This is just some technicality. We embed this into our favorite combinatorial object. I will say a few words about each of these arrows. And then, what do we do next? This is by far the hardest part, and also the one that's not natural. That's quite tricky. This we embed into the delta 0 subsets of, but not 0, 1, but to some weird compact metric space. Okay, so let me just define this. So this is the square, unit square, and this is the space of compact subsets of the unit square equipped with the Hausdorff metric. Okay, so compact subset of 0, 1 squared with Hausdorff metric. And as one would guess, this is number 4. From now on, these are just technical steps. Okay, it's not a one-line proof. I was lying. This is a two-line proof. So this, just as above, we already noticed that x plays no role. So x can be changed into anything else. Here we have a compact metric space, and that can be replaced by anything. So it's the delta 0 subsets of the Cantor set under inclusion, which embeds into the delta 0 2 subsets of x, which embeds into the Baire 1 functions on x. So this is essentially the structure of the proof. Okay. Well, once you do this, we are done, because yeah, it has at the very beginning and the very end, it has the Baire functions, and in the middle, it has this combinatorial linear algebra. Okay, so what do I want to say about the arrows? The arrows. So one, if you are familiar with the Hausdorff-Kuratowski analysis of delta 0 sets, so Hausdorff and Kuratowski did the following. Whenever you have a transfinite decreasing sequence of closed sets, and you take the union of every second ring, okay, so for the even ordinals, you take the union of f alpha plus 1 minus f alpha, or something like this, every second ring, then you can show that you get a delta 0 2 sets. An F sigma set, because this is quite clearly F sigma, a countable union, but the complement also looks exactly like this. So the complement is also F sigma, so this is a way to get interesting delta 0 2 sets. And this analysis just tells you that this is all the delta 0 2 sets you can think of. And moreover, in a way, you can generate from a delta 0 set this sequence in a rather natural way. You take closures, boundaries, whatever, and so on. So you take a canonical such sequence to every delta 0 2 set. And this already should explain something about this alternating lexicographical, because if a set is bigger and you do this resolution, this representation with these sequences, if the set is bigger and the sequences are the same up to some point, but then they suddenly split, then what happens is that for bigger sets, if they split at even ordinals, then you get bigger elements of the sequence because you take every second ring. So f alpha plus 1 minus f alpha. So, but if it's in even steps, then it reverses. This is the real reason. But what we are actually using is not this, because we don't have sets, we have functions. And so there is a Kekris and Luvo. Kekris and Luvo developed this theory for functions. And so they proved, I won't even give the exact details because this is quite cumbersome, that if f is a Baire 1 function, then you can, again, in a quite canonical way, write f as an alternating sequence alpha less than some psi of some functions f alpha, and these functions are upper semi-continuous. So this is somehow it's harder to comprehend if you have never seen that. But what Hausdorff and Kuratowski did for delta 0 2 sets and closed sets, that Kekris and Luvo repeated for Baire 1 functions and upper semi-continuous functions. And once again, because this is an alternating sum, okay, so this sum is quite weird. I mean, you have to define it. It's a transfinite sum. You have to be very careful. Lots of technical details here. I'm skipping everything, but still, the idea is there. If the function is bigger, and then you have this, you start generating this representation because there is this kind of an algorithm. That's very important that you have a kind of algorithm to generate this sequence. So if you have an f and a smaller g, when the procedure splits for f and g, then this sort of respects this alternating order. So I couldn't really explain it, but somehow this explains this outliers. Why this is natural. So this is what we do. I think you can sort of believe me that this is doable. And then to every function you assign this sequence, USC sequence. Yes, they will be decreasing. It's in the theory. I didn't even write it down. They will be strictly decreasing. You add the 0 and the very end. Blah blah blah. This is exactly the outlier. So this is all I can say about 1. Well, 2 is some simple technical step. What you actually do is that you take USC with the pointwise ordering, the upper semi-continuous functions with the pointwise ordering, and that. So not only the sequences you can embed into the sequences, but coordinate-wise, you embed the USC functions into 0, 1, and then this suffices for the sequences. Okay, and how do you do this? First, you embed this into what? Into the closed subsets of X cross R. How do you do that? The function f, you simply have to assign its subgraph. USC functions have closed subgraphs, and this is clearly a monotone map. And then to closed subsets, to what you want to assign numbers, how do you do that? To a closed subset f, you assign the following. The sum of, no, it's in the wrong order. Sum for those ends that un intersect f is empty of 1 over 2 to the ends, where un is a fixed basis of X cross R. Is basis.
Empty or non-empty?
I think it should be empty.
Empty.
Basis of, but let me check, X cross R. So what do you want to do? You to closed sets, you want to assign real numbers such that if your closed set gets bigger, then you assign a smaller number. And if your closed set gets bigger, then there are fewer terms here. So I think this is correct. Yeah. Okay, and then this is a complete proof for this not so interesting arrow embedding. And here comes in a really interesting part, but I cannot say too much about that. That's the heart of the matter. So you have this order, and you have to come up with a set of Baire functions. Okay, not even Baire functions, characteristic Baire functions. I'm hoping I put it there. Yeah, characteristic Baire functions ordered exactly this way. So what you do is that on the one hand you use this Kuratowski-Hausdorff argument. So because your sequences, so you have this tree, you have these sequences, and then you start assigning to these sequences somehow closed sets, so that along the branches you get this decrease in closed sets and you assign these. But somehow this does not work, and so that's why you get that compact set. And a very rough idea, not explaining the exponents too, just compact set to 0, 1. So whenever you have a sequence, try to assign these compact sets, the range of these ones. This is an attempt. Okay, this range is not in it's a compact set. Oh, it's a compact set if the functions are continuous. If the transfinite sequences are continuous sequences, then these are compact sets. They are not continuous. So that's why this is just a very rough idea. That's why you need the second coordinate and so on and so on. So this is still a subset of 0, 1. Let's cheat. Let's assume everything is continuous. Then this is clearly a monotone embedding. Maybe I flip the order.
Less than there, is that the alt x less than, or?
Yeah, absolutely. And then you have to show that that's 0, 2. And for this you need this Hausdorff, Kuratowski, whatever. Okay. And the rest. So this is the key part. I mean, that's a very, very, very delicate construction. You have to be careful. That's the key part. And then you are essentially done. So wants to show what? That the delta 0, 2 subsets of this compact metric space can be embedded into delta 0, 2 subsets of the Cantor set. How do you do that? This is a compact metric space. So there exists a phi which maps the Cantor space into this compact metric space in a continuous and onto manner. Right? Every complex metric space. And then what do you do? Once you have a set, you assign to it the pre-image. Because this is onto, this is strictly monotone. This is monotone for sure, because this is a monotone operation. Because it's onto, it's strictly monotone. Because this is continuous, it preserves that to 0 sets. And so that is this simple. And then what do we have? We have 5 here. That's essentially obvious, right? So every uncountable metric space contains the Cantor's a homeomorphic copy of the Cantor set. So whenever you have a set here, you just put that here, and this is a monotone operation. And this is, you just assign the characteristic functions to the sets. And this is sort of the end of this sketch of the proof. Well, I must mention, at least without writing down, a few interesting open questions. So now that we have this universal linear order, we have to reconsider whether this Baire 2 and Borel is so hopeless or not. So why couldn't we? Okay, of course, there won't be a ZFC answer that something is representable by Borel functions if and only if it's a very simple thing. But it is quite conceivable that for the Borel sets, there is another concretely definable universal linear order. And then the independent stuff only comes later. I mean, this could be a ZFC result, and then independence only comes from the fact that who is embeddable into this linear order, I don't know. And moreover, this plan is also there. I mean, it makes some sense. So replace this with Baire alpha. Okay? Okay, this is not USC, and unfortunately, the Kekris-Lubos theorem only exists for Baire 1, but because of this reason, we managed to generalize it, the Kekris-Lubos result, to every Baire alpha. So number 1 is done in the Baire alpha case. Well, after that, only question marks. So we do not know yet, but I think this is a good question. So is there a universal linear order for the class of Borel functions, for the class of Baire 2 functions, whatever? I find this conceivable. Okay, thank you very much. Are there any questions or more comments? Yes, there will be.
I can offer you a proof.
Okay, for what?
The Suslin line doesn't end.
The Suslin line?
Doesn't end. You were telling me that you are getting the first proof, ZFC proof, but there's another one. Komyat's result.
Forcing free proof.
Forcing free proof.
Of Komyat's result.
Okay.
So you take this Suslin line, take this pointwise closure. Yes, size continued, right? Compact set of size continued.
Okay.
There's a theorem which says that pointwise closure of Baire class 1 either has a size to the continuum or is inside the Baire class 1.
I
see. This pointwise closure is inside the Baire class 1. But now use the fact that the compact sets in Baire class 1 factor has a dense initializable subspace.
Okay, but this is not an easy proof.
No.
I mean, not as easy as Komyat's, not as short.
Still, it's a proof. Yeah. Actually, that in the paper I have lots of open questions, and one of them is that I always have the feeling that this whole theory should have to do with this Rosenthal theory. So far, I've never found any connections. I'm just believing there should be one.
But it should be somehow.
Yes, and so this is a good instance.
There is a very beautiful result which says if you have a class of functions, Baire class 1 function, look at its closure is either inside Baire class 1 or it contains copy of beta n.
Yes. Exactly. Okay, any more questions? Thank you. Thank you.